Welcome to Spring LIB.
We're asked to prove Snell's law using optimization. So the background is V1 is the velocity of light in air, and V2 is the velocity of light in water.
That was the gayest shit you could do back then. I would love to write it.
And V2, this is velocity.
I remember hearing the story of Lady Godiva when I was a kid. My dick got so hard. Really? We're getting fucked by a horse.
According to Fermat's principle, a ray of light will travel from a point A in the air to a point B in the water by path ACB that minimize the time taken. We're asked to show that the sine of theta 1 over the sine of theta 2 equals V1 over V2, where theta 1 is the angle of incidence and theta 2 is the angle of refraction. As is shown in the figure in exercise 71 of this section. And so this equation, the ratio of the sine thetas equals the ratio of the velocities, is known as Snell's law. To prove this, first we'll use the Pythagorean theorem. By the Pythagorean theorem, if we use the figure in the book, we have the distance from the point in air A to C, where C is the point on the surface of the water, is the square root of a squared plus x squared. And the time it takes light to travel from A to C, we'll call this TAC. This is this distance traveled divided by the velocity, or the square root of a squared plus x squared over V1, since it travels through air. Now I'll take the derivative of t with respect to x by using the chain rule. So t prime ac of x, this is 1 over v1 times 1 over the square root of a squared plus x squared. I'm sorry, this should be x over square root of a squared plus x squared. Now we'll use trigonometry and the length of AC to find the value of sine of theta 1. This is using triangles x over the square root of a squared plus x squared. Now I'll plug sine of theta 1 into t prime of AC. So we have t prime of AC of x. Well, this is actually equal to 1 over v1 times the sine of theta 1, which you have to remember in this case, theta is a function of x. Now, likewise, by Pythagorean theorem, we have the distance from B to C, from under the water to the surface point, is the square root of b squared plus c minus x squared. And likewise, to find the time it takes to travel from C to B, t sub bc, well, this is the distance, square root of b squared plus c minus x squared, divided by the velocity of light in water, v2. Once again, I'll find the derivative, t prime bc of x. This is 1 over v2 times negative x minus c. or sorry, negative, what is this?
Fuck yeah. It's like, who gives a shit?
Negative c minus x
None of you watched it. It's all just symbolic.
over the square root of b squared plus c minus x squared. And now again, using trigonometry and the length of BC, we find that sine of theta 2 is equal to c minus x over the square root of b squared plus c minus x squared. And plugging sine of theta 2 into t prime of bc, we have that t prime of bc of x is 1 over v2 times negative sine of theta 2.
Look at all my cool clothes. I haven't done any of the missions. 3 outfits?
Now we have that
So there's this one, the Earl. The Earl? Oh, hell yeah, this being gay. Well, this one's great because it's like, there's, if you run
the time from a to b is the same as the time from, the time from a to c. No, it is the time from a to b is the same as the time from a to c plus the time from c to b. But of course, this ordinary equation implies that the differential equation t prime of ab x is equal to t prime ac of x plus t prime bc of x as well. And so therefore we have that this is equal to t prime ac of x, which we found was sine theta 1 over v1, and then t prime bc of x is negative sine theta 2 over v2. And now, by Fermat's principle, we want to find the path that minimizes the time taken. So we want to find the value of theta, I guess you could say, or the value of x, such that t prime of AB equals 0. And therefore, we obtain that the sine of theta 1 over v1 equals the sine of theta 2 over v2. And this is Snell's law.